All right, here is our last video of chapter 13. We are going to be looking now a little bit more at that rate that we were looking at, and that we said the rate has K, okay, a constant, rate constant, times the concentration of the reactants. We're going to look at that. A lot of this comes into the mechanism, the specific mechanism that's going on, how the molecules are colliding and going from reactants to products. So we'll look at that. We'll look at some data and try to put this all together. All right, so first thing we have, let's just recap what we did before. At a given temperature, the number of collisions is proportional to the product of the reactant concentration. So here is a general reaction. We have A plus B gives us P. So A and B are reactants, P is a product. And we just said that the reaction rate is equal to some constant K, okay, at a given temperature, times the number of collisions per unit time. And the number of collisions per unit time will increase if the concentration is increasing. So this means the higher the concentrations, the faster the rate. And this is specifically the higher the concentration of reactant molecules. So we are looking at a forward reaction. What will affect the rate of that reaction? All right, so the number of collisions between A and B can be expressed as the concentration. Okay, and when you see these, I think I've said this before, but just to make sure, brackets around something, this means concentration. So concentration of A, concentration of B. All right, so the collision between A and B per unit time is proportional to the concentration of A to some order times the concentration of B to some order. Now, for my 103 students here at IU, I told them to draw an arrow here, draw an arrow there, and then I said to go back and make big X's all over that, because that is totally not right. So you do not, okay, take the coefficients in a balanced reaction and assume those are the orders. You cannot do that. All right, so not how that works. How do you find those orders? Okay, these are the numbers here, the X and Y. This has to be from actual experiments. Find experimentally. Now, we talked really early on in this video series of chapter 13 about reaction mechanisms a little bit. We talked a little bit about a slow step, okay? And so the number of collisions, the rate is gonna be affected by the slowest step here. So the concentrations, you need A and B to make the products, but the reaction might be faster based on A concentration if A is involved in the slow step of this reaction. All right, and so we can only find that out experimentally. So we'll look into that a little bit more. But without doing the experimental stuff, you can write a general reaction rate. And a general reaction rate doesn't have numbers here for the orders. It just has X, Y, X, Y, Z, depending on how many reactants you have. So here it is. Your reaction rate is equal to the constant K, the rate constant, times the concentration of your reactants, each raised to some order. Now, the orders, we would say, can be usually first, second, third. Okay, they don't usually get too much higher. Sometimes it's zero order. And the total order overall, you would just add up the order. So if X equals 1 and Y equals 1, and you found those experimentally, if you found those, you would say this reaction is second order overall. Oops. There we go. All right, so that's kind of generally how that works. So let's just use a real reaction here. So we have 2NO plus O2 gives us 2NO2. We have the valence equation. You do not just assume that the 2 and the 1 right here in the valence equation are the orders. You have to do the experimental data to figure that out. But we can write a general rate law, and we know that the rate is equal to some constant K times the concentration of the two reactants, NO, both raised to some order. We'll call that one X, and then O2, Y. All right, so this tells us that the higher the concentrations of NO and O2, the faster the rate of this reaction should be. All right, let's look then at these rate laws in general. Okay, so like we just said, okay, the coefficients there do not just go in and are the orders for the reaction. You have to do that experimentally. We'll look at some studies in a minute, but what you do is you do a bunch of similar reactions, okay, where you just take one time and you hold the reactant concentrations constant, and then the next time you change one of the reactants and see how it affects the rate. Now, when we're talking about how it affects the rate, you can measure that. All right, we just said that the rate is equal to the concentration of reactants raised to some order times the rate constant, but you can also talk about how the rate is the change in product concentration over time. So over time, the rate will change, and you can measure it by how much product you make per time, and that will show you how the reaction goes. All right, so let's just put this all down here. So the rate is the change in product concentration per time, and if our reaction is going, let's just go to that similar one we just said, A plus B goes to product. We could also then write what we just were doing before, rate equals K times the concentration of A times the concentration of B, and since it's just our general and we don't know what it is, we'll just put X and Y here. So this and this are equal to each other. So you can measure the concentration changes of A and B, if you know K, and this should also then equal the concentration of change in product concentration per time as well. Looking at change in product concentration, this will have a unit of molarity, and this will be per time, and time will be in seconds. So this is molar per second will be your units on rate. What will be your units on A and B? All right, well, it'll depend a little bit on what the X and the Y are, but the concentration will have units of molarity, which is just a capital M there. And so depending on what that is, K could have different values. So that's one thing you might have to figure out is what are the units on K, and it could change depending on if it's first order, second order, third order of the reaction overall. All right, let's look at some data and see how they actually come up with these rate laws. All right, so here we have three reactions taking place. All of them have the same reactants and products, so it's the same reaction, but what we are doing in each of these is just changing the concentrations of the reactants. So our reactants are A and B, and we're making product, and they're written in moles, but they're all in a 1 liter vessel. So when you see 1.0 moles of A, you can just assume that's 1 molar A. And then we can see that there's a certain amount of time, okay, so this is per unit time. So after 1 minute, you are able then to measure the moles of A, B, and P. All right, so just looking at this first one right here. All right, you start with A and B, 1 mole of each, no product at this point. Boom, reaction takes place, you mix A and B together. At 1 minute, you stop, you measure the concentration of A and B and the concentration of P. And you can get your rate from there, because the rate would be the change in concentration of P per unit time. Okay, so you can calculate that. You know it's 0.1 mole, you know it's been 1 minute, and you're in a 1 liter vessel, so you can find that. Let's see how this reaction is different from the second one, and then we'll look at the third as well. In the second one, what are you doing? All right, so moles of A has increased. We went from 1 mole to 2 moles, but the moles of B stayed the same. So look at how much P you've made. Is P the same, or has that gone up as well? So we did make before 0.1 moles of P, but when we doubled, okay, this went up, A went up by 2, A times 2, okay, so we increased the concentration of A times 2, P, the rate, okay, of making P, went up by 2. All right, let's go to the next one a minute, and then we'll come back and talk about what these mean. All right, in the third reaction, A is starting at 1 mole, okay, so it's back to the same as it was in the first reaction. This time, we're just changing B. So any change in rate comes from the concentration of B, is due to the concentration of B. All right, so when B goes up by 2, what happens to the rate? You can see now you're at 0.4 moles divided by a 1 liter per 60 seconds here. Our rate has gone up by 4. So when B doubles, the rate goes up by 4. All right, so let's talk about these orders a little bit more detail. Order of 1, let's do that one first. All right, an order of 1 means that there's a 1-to-1 correspondence between the reaction concentration and the rate. You can see this in A. When we doubled A, the rate doubled. So it's a 1-to-1 correspondence. If we tripled the concentration of A, the rate would go up by a factor of 3 as well. So this right here, when this went up by 2, this went up by 2. This is a 1-to-1 correspondence. Which means first order for A. All right, then let's look at the second order, and this is demonstrated with B. All right, from Bessel in experiment 1 here, where B was 1 mole, to now when we doubled the concentration of B, our rate went up by a factor of 4. Okay, so that indicates that we have a second order. All right, the rate quadruples when the concentration of the reaction or reactant is doubled. So here's a little demonstration here. When you have the concentration of B and you are multiplying it times 2, that little subscript there, or superscript of 2 indicates second order, and that 2 to the squared is 4. So that's showing that it's quadruples when the concentration is doubled. All right, so this is what is happening in B. And we can then write our rate law. Okay, so the general rate law was the rate is equal to K, some concentration, the concentration of A, concentration of B. And now, using this experimental data, we have now figured out what X and Y is. X is 1, Y is 2, and so now we can write the correct rate law. So rate equals K times the concentration of A to the first times the concentration of B, and B is second order. So I would say A is first order, B is second order, and overall this is a third order reaction. Okay, you just add up the superscripts there. One thing we didn't talk about was the zero order, and this happens when you would double a reactant and then you look at the rate and the rate doesn't change. That means that the reactant that you were doubling or increasing in concentration has no effect on the rate. Okay, it might not be involved then in the slow step of the reaction. So you can keep increasing it, but since it's not involved in the slow step, it's not affecting how fast this reaction is going. So that would happen if you increase the reactant and there was no increase in rate. I'm sure there'll be some other ones that you'll see that in action. Let's look at some data. Okay, it's kind of laid out a little bit more organized fashion than with the pictures in the boxes, but here is 4 experiments that were done. And the reaction is the 2NO plus O2 gives us 2NO2. And we can then write the general rate law for this. Let's do that first. All right, it's equals to the rate constant times the concentration of NO, we'll say to the X, times the concentration of O2 to the Y. Now, we cannot just assume that X is 2 and Y is 1. Okay, that is not what you can do. You have to use actual data, experimental data that shows you how the rate will speed up or increase by changing the concentrations. All right, sometimes it is the case, but you want to make sure that you don't just automatically pull those numbers over. All right, so we are looking at NO and O2 are 2 reactants. We have several different experiments where we are showing their initial concentration, and then over time we were able to measure the rate of formation of the product. Okay, so we can see how much of this has been produced. Let's figure out which experiments we want to look at to see how the concentration of NO affects the rate. So for that one, we want to find two experiments that NO increases by a factor, but O2 stays the same. It looks like there's probably two places that you could look for this, okay? But let's just look at experiment 1 and 2. So in experiment 1 and 2, the concentration of NO goes up by 2. It went from 0.015 to 0.03. And the concentration of O2, constant. So the only change in rate is due to the NO. It's not going to be due to the O2 because that stayed the same in both cases. So now you want to compare the two rates, okay, for those two experiments. And usually you just take the bigger one, divide it by the smaller one, and see what it went up by. All right, so if you take that, you will see that NO has gone up by a factor of 4. All right, so if it's gone up by a factor of 4, what does that mean for the order of NO? All right, when NO goes up by 2, it went up by 4. That means that NO, or the X there, is a 2 for second order. All right, then let's look at another set of experiments. In this case, we want to hold NO constant, but only change O2. So which two would you want to look at for that? I think maybe I would look at, I'm going to change color. Let's see, in experiment 2 and experiment 4, the NO is constant at 0.03 molar. And in this one, our O2 has gone from 0.015 molar to 0.03. So this is concentration of O2 times 2. So if we are doubling O2, what effect does that have on the rate of this reaction? All right, so the two rates we're going to be looking at are these two right here. You want to divide the 0.384 divided by 0.192, and you will see that the rate went up by 2. So when you doubled the concentration of reactants, the rate went up by 2. That's a 1-to-1 correspondence. That's telling us that Y is 1, and it's first order for O2. All right, so then now that you have those, you can then write your rate law. Rate equals K NO2 O2, and you can include the 1, or you don't need to include the 1 there. It would just be assumed that it was 1. Rate is 1. At this point now, since you are given these values, okay, for NO and O2, and you know what they need to be raised to, and you're also given a rate, you can plug in values and solve for K. So you just pick one of the experiments to do, and we'll switch to a different green. Let's just pick this one right here. You would throw in the 0.03 molar for NO, and then you would square it, and you would plug in the 0.03 molar for O2, and that's just raised to the 1, and then you would plug in the rate right here in molar per second right here, and then you can easily solve for K. Now this K is a constant, so guess what? You could have also picked experiment 3, 2, or 1, done the same thing with the initial concentrations and the rates, and you should get the same number for K in each of those cases. All right, we have another one to look at. So this one right here is another reaction. This one actually has 3 reactants, so you had to find the rate order for all of them. There's a bunch of experimental things going on here. Okay, there's 4 experiments. The initial concentrations are listed in the rate. I'm going to take a little break. I want you to try to solve this on your own. Pause the video, come back with your answer, and in addition to just finding the rate and the overall order, why don't you plug in some values once you solve it and figure out what K is. All right, I have solved this problem. I hope you have gotten it correct as well. You need to look at the different experiments one by one in a way that you will only change one reactant at a time. All right, so sorry it's a little bit messy here, but the first thing I did was I looked at experiment 1 and 2 together. In this experiment, you can see that the BrO3 minus doubles in concentration, but the other two reactants stay the same. Any change in rate then comes from the change in concentration of the BrO3 minus. When I doubled the concentration, the rate went up by a factor of 2. That's a 1-to-1 correspondence, so we are first order for BrO3 minus. Do the same thing now looking at the second reactant only. So I looked at experiments 2 and 3. In this one, I can see that the Br minus increases by 2, where the BrO3 minus and the H plus are staying constant. When I look at the rate change, it goes up by a factor of 2. So when I increase the concentration of Br minus by 2, the rate also goes up by 2, so we're first order for Br minus. All right, the next one, I looked at experiment 1 and 4. And the reason I picked these two experiments to look at is the BrO3 minus stays constant at 0.1 molar, and the Br minus stays constant at 0.1 molar. So the only concentration that's changing is the H plus. It goes from 0.1 to 0.2, so it increases by a factor of 2. And when it does that, if you divide the rates of the fourth one to the first one, it goes up by a factor of 4. All right, so that tells me that when I double H plus concentration, the rate increases by a factor of 4, which is a second order reaction here. So I have my rate. You can see that it is fourth order overall, okay, if you add up the 1 plus the 1 plus the 2. So that is how you go about using the data, figure out what the order is and the rate law for the reaction. All right, last thing, I could have picked any of the 4 experiments and I could solve for K. I picked the first one because it was right there and easy. And I know that K, okay, if you want to isolate this by itself, you just need to divide both sides by the concentrations to get K by itself. So K is equal to the rate divided by the concentration of the 3 reactants, all raised to their order that we have figured out. I plugged in the numbers, okay, so these numbers all came from right here for the concentrations. They were 0.1 for each of them. That made it easy, so it's 0.1 times 0.1 times 0.1 squared, all right, because H plus was second order. And then the rate would be this initial rate here in molar per second. Plug that in. All right, check how the units cancel here. We mentioned earlier that K will have different units depending on what order the reaction is. It's molar per second, and then when I divide it by the molar times molar squared, that's molar to the 4th. One of the molars cancels out. All right, and so now we have the molar cubed on the bottom, on the denominator, and seconds is on the denominator. So when you work this out here, you have molar to the -3, and this is times then seconds to the -1 as well. All right, that hopefully should be good for finding this kinetic data. It's kind of fun to do and figure out. And that leads us to the end of chapter 13. So we have gone through a lot in this chapter. Energy profiles, looking at endo-exothermic activation energy, the things that speed up a reaction, what you can do to change those, and then how to use kinetic data to then figure out what the rate law is. Some of this stuff will carry over to the next chapter, and we'll get going with that next.